In this video, we're going to look at some examples of converting between the wavelength, frequency, and energy of electromagnetic radiation. So in order to do this, there are two equations that we need. The first one involves the speed of light, and it is that the speed of light of any wave of electromagnetic radiation is equal to its wavelength times its frequency. Now, this funny-looking upside-down Y is the Greek letter lambda, and this sort of script-looking V that represents the frequency is the Greek letter nu. So I would say that C is equal to lambda nu. And the speed of light, which I will give you, is 2.998 times 10 to the 8, and it has units of meters per second. So the units on wavelength need to be in meters, and the units on frequency need to be seconds to the -1, or sometimes that's called hertz. And then the other equation that we need is that the energy of one photon of electromagnetic radiation is equal to a constant that we call Planck's constant times the frequency again. And the units on the energy of the photon are always going to be in joules. Planck's constant has units of joules times seconds, and the frequency again needs to have units of seconds to the -1. So let's look at a couple examples. All right, so we're asked to calculate the frequency of light or electromagnetic radiation that has a wavelength of 750 nanometers. So I know that the relationship between wavelength and frequency is that C is equal to lambda nu, where the speed of light is 2.998 times 10 to the 8th meters per second. But my wavelength needs to be in meters, not nanometers. So I need to do that conversion first, and then I can plug those numbers into my equation and solve for the frequency. So I have 750 nanometers. I know that 1 nanometer is 10 to the -9 meters. And so when I multiply that out, I get the wavelength is 7.5 times 10 to the -7 meters. All right, so I'm going to take my equation here, and I'm going to solve that for nu. So I'm going to divide both sides by lambda. So the frequency, nu, is C divided by lambda. So I plug in the speed of light, and the units are meters. It's meters per second, so I can also write that as meters times seconds to the -1. Divide that by the wavelength. And my meters cancel out. And so my frequency comes out to be 4.0 times 10 to the 14, and it has units of seconds to the -1, or 1 over seconds. And that's what we would expect for units on frequency. All right, so I've got one more example on the next slide. In this example, we're told that a photon has an energy of 5.43 times 10 to the -20 joules, and we want to know the wavelength. So I know the equation for the energy of a photon is E is equal to h nu, or E is equal to Planck's constant times the frequency. So that doesn't involve the wavelength, but if I can get the frequency, I know that the speed of light is the wavelength times the frequency. So if I know the frequency, I can get the wavelength. So the first thing I need to do, get the frequency. So I'll take the first equation, I'll divide both sides by h. So the frequency is energy divided by Planck's constant. So the energy is 5.43 times 10 to the -20 joules. Divide that by Planck's constant. It's joules times seconds. So my joules will cancel. I'll be left with 1 over seconds, or that's the same thing as seconds to the -1. So my frequency comes out to be 8.19 times 10 to the 13th seconds to the -1. All right, so now I can take my second equation. I'm solving for lambda, the wavelength, so I'll divide both sides by nu, the frequency. So lambda is the speed of light divided by the frequency. So I have again, the units on speed of light are meters per second, or meters times seconds to the negative 1, divided by the frequency. So my inverse seconds cancel. I'm left with meters. So my wavelength is